Good morning, Chem 20s. Our lesson today is going to be on dilution. You are already going to come in with a little bit of knowledge on dilution because of experiences you might have at home. Think, for example, of frozen concentrated orange juice. In order to dilute it at home, you would have added water. You would add more solvent. That in itself is going to decrease the concentration of this orange juice. Now, again, when you get it out of the freezer, you would open it up, you would put the concentrated juice, the container full, into your pitcher. You would then add three or four, filling the container, 3 or 4 cups of water in order to dilute it down. Your mothers probably didn't let you just eat it straight out of the container. Maybe you were allowed to lick the lid, but in all honesty, it was just way, way, way too strong. And so by adding this extra water, by adding this extra solvent, you diluted it by making more room for more water. Now, we use this in real life applications all the time. And in most cases, I would like to think it's environmental, but in a lot of cases, it's also for cost. So if you think about it, if I could order acid for Crescent Heights High School. I use all sorts of acids starting in grade 7. We have zero point 0.1 mole per liter, zero point 0.5 mole per liter, 1 mole per liter, 3 mole per liter. But it would cost a lot for us to buy all those separately because ideally, if you're thinking about it, you're paying for a lot of water in that acid, right? If we bought the concentrated acid and paid for the shipping and weight and how much room it would take up in the shipping container, right? When we received it, I now could dilute it myself by adding water and doing the calculations we're going to learn today to get any concentration I want. I have more variety for me, but I also am able to ship a stronger substance, shipping less water ideally, right? I'm not going to dilute it down. So I'm going to reduce the size of the containers. I'm going to reduce how much room and weight this substance is because I'm going to take out that water because I can do those calculations and make the solution less concentrated myself. So if we take a look example, again, I would like to look at the initial solution compared to final solution. You'll notice to get the final, we added more water, we added more solvent, but you'll notice that we start with 7 particles of solute and we end with 7 particles of solute. The number of moles or the mass of the solute before and after we start is going to be the same. All we're doing is adding water. So we are diluting it. The same amount of solute is getting diluted by adding more solvent to this solution, which means because of this connection of before and after dilution for number of moles of solute, there is a formula that can come from this. C1V1 equals C2V2. In this formula, C1 stands for the initial concentration. V1 stands for the initial volume of this solution. C2 then is, of course, the final concentration of the solution, and V2 is going to be the final volume of the solution. Now, like in most of the formulas we've done, V1 and V2 can have any unit they want for volume. Milliliters, milliliters, liters, liters, kiloliters, kiloliters. What's important is the unit is the same for both the initial and the final volume. This is also true for concentration. And in concentration, we get a little bit more variety because we've looked at concentration in a number of ways in the last week. We've looked at it as molar concentration in moles per liter. We've looked at it as very, very minute substances like parts per million. And we've also looked at it as liquids dissolved in liquids as percentages. And the key again is as long as both concentrations are the same unit, units do not matter in this case. So what I would like us to do is let's do example number 1. So water is added to 200 milliliters of 2.4 moles per liter of ammonia cleaning solution until the final solution is 1,000 milliliters. What is the molar concentration of the final diluted solution? So let's get and make our list of variables over here. So we have V1 is going to be 200 milliliters at a concentration of 2.40 moles per liter. And we're going to add water until the final solution, so V2 is going to be 1,000 milliliters. We would like to know what is the concentration of this diluted solution. So again, I look here, milliliters, milliliters. I like that, moles per liter, which means my answer is going to be in moles per liter. My new memorized formula is C1V1 equals C2V2. We're going to solve for C2. So we're going to move V2 to the bottom. So to find the final concentration, we're going to take the initial concentration times the initial volume, divide by the final volume. So take 2.40 moles per liter, multiply by 200 milliliters, and we're going to divide by 1,000 milliliters. So I'm going to take 2.4 times 200 divided by 1,000. I go back to the question 435. So I'm allowed 3 sig figs. So my answer is going to be 0.480 moles per liter. Now, because concentration is something we innately have an understanding of, I really want to make sure that our answer makes sense. So we added a lot of water to go from V1 to V2. By adding this water, we would expect our concentration of our ammonia solution to decrease. So we would expect our answer to be below 2.4. And it is well below 2.4, so we probably know we did the answer correctly. So 1 mark is for the 2 formulas, 1 mark is for substitution with units, and 1 mark is for answer in units in correct significant digits. For question 2, I would recommend copying down the question, pausing the video, and then unpausing the video to check your answer. So I have 65 milliliters of a 0.759 moles per liter solution of sodium chloride. I want to figure out the final volume. If we diluted it to a concentration of 0.200 moles per liter. So I have my memorized formula, C1V1 equals C2V2. This time we're going to solve for V2. So we're going to move C2 to the denominator. V2 equals, take your initial concentration, multiply it by your initial volume, divide it by your final concentration. So we're going to take 0.759 moles per liter, multiply it by 65 milliliters, divide it by 0.2 moles per liter. So 0.759 times 65, enter, divided by 0.2, enter. Again, 2 sig digs, sorry, 3 sig digs, 3 sig digs, 3 sig digs. My answer for final volume is going to be 247 milliliters. Again, I want to think about this. My concentration decreased. The only way for my concentration to decrease is for me to continue to add water. So that means my volume has to increase. So it's got to be more than 65 milliliters. 247, odds are we did the question right. 1 mark for formulas, 1 mark for substitution with units, 1 mark for answer with units in sig digs. Last question, example 3. Again, you should probably try this one for yourself and then join me to check the answer. So a student adds 500 mils of water to a bucket containing 450 milliliters of 6.5 moles per liter sodium chloride solution. So my initial volume is 450 milliliters. My initial concentration is 6.50 moles per liter. Now, to that, I am going to add 500 milliliters. So I started with my 450. I'm going to add 500 milliliters. So I'm going to end up with 950 milliliters as V2. So I am then going to go find what is the concentration of my new solution. So C1V1 equals C2V2. We're going to find concentration this time. So I'm going to move V2 to the bottom. So to find final concentration, take your initial concentration times your initial volume and divide by your final volume. So 6.50 moles per liter concentration times 450 milliliters divided by 950 milliliters. So 6.50 times 450, enter, divided by 950, enter. And we are allowed 443. So we're allowed 3 sig digs, 3.08. And this is going to be moles per liter. Again, let's think of our answer. We added a lot of water. So our volume went up, which means my concentration should drop from 6.5, and it did to 3.08. So my answer makes sense. 1 mark for formulas, 1 mark for substitution with units, 1 mark for answer, sig digs, and units.